So, hello everyone, this is Maurizio, editor of Power Electronics News and eWeb. Today, I have the pleasure to talk with Ronald Mallett, Professor Emeritus at University of Connecticut. Hi, Roland, how are you? And thanks a lot for coming here.
Oh, I'm doing fine, thank you. And it's a pleasure for me to be with you.
Thanks a lot. So, today I would like to talk with you about the meaning of time, this strange, this nice, wonderful concept. But before going into the details, before starting, please introduce yourself, Ronald, and your great career.
Sure. Yeah. Well, I'm a professor emeritus at the University of Connecticut. My name is Ronald Mallett, PhD from Penn State University. And I'm also a research professor. And my specialty is, I'm a theoretical physicist. My specialty is Einstein's general theory of relativity. Things like black holes, the Big Bang theory of the universe, and time travel.
Nice, fantastic. So, time travel. Time is one of the 7 fundamental physical quantities. So, time has long been an important subject of study in religion, philosophy, and science, of course. It takes the indefinitive continued progress of events. So you spend you spend a great deal of time thinking about time. So
right.
What's the meaning of time for you?
Well, the thing is that you were absolutely right that this is a question that is as old, really, as mankind. I mean, one of the great philosophers, St. Augustine, said, in fact, that if no one asks me, I know what it is. But if someone does ask me, then I don't know what it is. And I think that that's it. I mean, we have an intuitive sense of what time is. And for me, I think of it as being, let's see, a shortcut, I would put it, is the persistence of existence, is the way that I put it. Now, what do I mean by that? Well, the thing is that something has to endure. In other words, if you have a three-dimensional object, in fact, this is something that was used as an example by H.G. Wells in his famous classic, The Time Machine. If you have a cube, for instance, it has 3 dimensions, okay? But if it doesn't exist in time, in other words, can an instantaneous cube exist? So to me, it's duration. Time is connected with duration. It's the persistence of existence. Something has to persist in order for it to exist. And that to me is what time is.
Excellent. So you mentioned time travel. Time travel fascinates us, and practically anyone would like to have the chance to go back and change something, thus challenging one of the biggest unknowns in physics, so time. What's idea about time traveling, and why are we looking for?
Okay, well, I'll tell you why I'm looking for it in particular, because people have asked me, why is it that I was interested in the whole subject of time travel in the first place? And it had to do with something that was a personal tragedy in my life that happened many decades ago. I grew up in the Bronx, New York City, and I was the oldest of 4 children. And my father was a television repairman in the Bronx. And the thing, for me, I idolized him. I mean, he worked very, very hard, but he spent a lot of time with the family. And I think that he was actually beginning to groom me to go into his field with him. And the thing is, and he gave me toys like, scientific toys like crystal radio set and a gyroscope. And the thing is that he looked healthy, he looked strong, he looked robust. We didn't realize that he had a weak heart. And he was a man who actually worked hard and played hard. And the thing is that he died suddenly of a massive heart attack. He was only 33, and I was 10 years old. And it devastated my world. It really crushed me completely. I mean, I was a happy kid prior to that, but after that, I became very depressed. And I was lucky that another gift he left me was a love of reading. He loved to read. And about a year after he died, when I was 11, I came across the magazine version of H.G. Wells's classic, The Time Machine. In fact, I have it over here.
Yeah, nice.
Yeah, okay. This actually changed my life because inside it said that scientific people know very well that time is a kind of space and we can move forward and backward in time just as we can in space. And when I read that, it was like the sky opened up. I thought, wait a minute, if we can move back in time, then maybe if I had a time machine, I could go back and see him again and tell him what was going to happen and change things. Okay. And of course, I mean, remember, I was 11 years old and I thought that it was going to be, something simple. In fact, my mother had kept the old radio and television parts of my father. And I tried to use the cover as a design with bicycle parts and, all kinds of things. And of course, it didn't work. But I remembered that it said scientific people know very well. So I knew science was going to have to play a role, but I didn't know exactly what that role was going to be. And so later, the second book that changed my life came along, and the second person that changed my life came along. I used to be a bookaholic. I would hang out in bookstores all the time. Okay, I just had to read, and I would go to this. There's a Salvation Army, which is they have clothes and they have books, and I could afford to get that. I should mention, after my father died, we became very poor, and one day I went in. And I saw the second book that changed my life. It was a paperback and it had a picture of Einstein on the cover. And Einstein was standing next to an hourglass. Now, I knew that Einstein was this great genius, but I didn't know exactly what it is that he did. And the thing is that since he was standing next to an hourglass, I thought maybe Einstein had something to do with time. So I got the paperback, and even though it was popularization, I didn't have the real background, but I did pick up the essence. Einstein said that unlike the classical physics of Newton, in Newton's physics, nothing can alter time. There's nothing you can do to change time. However, Einstein said there are ways that time can be altered. And that, I said, oh, I have to understand Einstein, because if I understand Einstein, then I might be able to figure out how time can be altered. Okay, so that was the beginning of my passion for Einstein. And as a matter of fact, Einstein's physics does allow for the possibility of time travel. And I should say, in a nutshell, the special theory of relativity allows for the possibility of time travel to the future. The general theory of relativity allows for the possibility of time travel to the future as well as to the past. And so that's why I became interested in the general theory of relativity.
So you were able to mathematically demonstrate that by using a beam of laser light in circulation, is it possible to have a twist of space and time. So can you tell me about your theory and others main about time traveling and of course your next projects?
Sure. Well, in order to explain this that I did, I have to go back and explain to you what Einstein did, because my work on Einstein's general theory of relativity. So in order to give a complete picture, we're going to have to step back.
Sure.
Okay. Einstein's special theory of relativity, in a nutshell, he developed that in 1905. And essentially, it said that time is affected by speed. The faster you move, the more time slows down. Time for a moving clock slows down. And also, he said that the speed of light, you might say, is the ultimate speed limit, okay, of any kind of signal propagation. Now, the thing is that we now experimentally, almost routinely, send elementary particles into the future. You know, devices like the Large Hadron Collider in CERN, they speed up subatomic particles. And sometimes these particles can live 10, 20, 30 times longer than they normally would, the closer we speed them up to. Now, the thing is that Einstein was confronted with a problem, though, because he wanted to apply his theory to everything, all the forces that he considered important. But the one that stood out was gravity. He couldn't fit gravity into the problem, okay? And to give you a simple example of what that means and why that's important is that let's think of, the Earth is 93 million miles away from the sun. Yep. And you know that it takes 8 minutes for light to get from the sun to the Earth, okay? Now, suppose there was a cosmic catastrophe that destroyed the sun. What would we see? And I mean that in that literal sense, because the thing is it would take 8 minutes for us to see the sun go out. However, according to Newton, gravity immediately shuts down. So you would have the weird effect of, since gravity shuts down, that would mean that the Earth would immediately be going off its orbit. So you would have the strange effect of being able to see the sun sitting in the sky, but the Earth would be going off into space. What that implies is that that gravity is traveling faster than the speed of light. So Einstein realized that he was going to have a whole new theory of gravity in order to solve that problem. And that's what his second theory, the general theory of relativity, is all about. The general theory of relativity is Einstein's theory of gravity. And what he said is that gravity isn't really a force. He said that gravity is an effect of space. And what he meant by that, and this is an example I use when I'm giving popular lectures. Suppose that we had a small rubber sheet, so let's say a trampoline. And suppose you put a bowling ball on it. It'll curve the rubber sheet, okay? Now, the thing is that if I put a marble on the rubber sheet, the marble will move down towards the bowling ball. Now, let's say the rubber sheet is still there, but it's transparent, okay? So what you have in that situation is you have the marble and you have the bowling ball, but you can't see the rubber sheet. Now you let the marble go. The marble moves towards the bowling ball, and you would say, haha, somehow the bowling ball is pulling on the marble. But you know that's not what's really happening. It's actually the bowling ball is curving the rubber sheet, okay? And in fact, if you give the marble a little bit of a sideways motion, you can get the marble to orbit around the bowling ball. And you would think that somehow it's the bowling ball that's doing that. Einstein said, that's an analogy, but Einstein said that's what the sun is doing. The sun is actually curving the empty space around it, and the Earth is actually just moving along that curved space. So according to Einstein, gravity isn't a force. Gravity is actually a property of curved space. And that's really important, because that is part of the basis of what my work is based on. Incidentally, according to Einstein, this bending, remember that in Einstein's work, space and time are connected to each other. Whatever you do to space also happens to time. That's why it's called space-time.
Yeah.
And what Einstein said is that this bending of space we see as gravity, but what about the bending of time? That shows up as clocks running slower in a gravitational field. The stronger gravity is, the more time will slow down. And we actually know this. In fact, one of the things that it has a practical implication. People don't realize it, but their GPS actually works because of Einstein's theory, okay? The clock in your unit is actually running a little slower than the clocks on the satellites that are sending the signals down. We have to take that into account, okay? According to Newton, that effect wouldn't occur. Now, my work is based on Einstein's work in the sense that in Newton's theory, the only thing that can create gravity is matter. The matter of the Earth keeps us anchored. The matter of the sun keeps the Earth in orbit. In Einstein's theory, not only can matter create gravity, but light itself can create gravity. Light is not matter, but light can create gravity. And that was the key to the breakthrough of my work, because if gravity can affect time and light can create gravity, then light can affect time. That is the core of my work. And what I realized is that there was a way that you could actually use this. Remember, I said that matter and energy can cause this bending of space, but there's a way that you can actually cause the twisting of space. That is to say that what I realized is that if you have a circulating beam of laser light, and when I say this, everything I'm telling you, I was doing with equations, by the way, okay? This is based on Einstein had created a set of equations called the gravitational field equations, okay? Very, very, very complicated set of equations. And what I did was I actually knew there was a device called a ring laser. A ring laser is actually a device that creates a circulating beam of light. You can think of having, let's say, a square with mirrors on each corner, and bouncing the light off of each of the mirrors, you can get a circulating beam of light, laser light, okay? Yeah. And what I did was I actually solved Einstein's gravitational field equations to find out what would happen to space and time within the region of the circulating light beam. And what I found was two different things happened. one, the circulating beam of light will actually cause a twisting of empty space. The way you could think of that is, suppose you have a cup of coffee and you think of the coffee as being like empty space, and think of your spoon being like the circulating beam of light.
Yeah.
Then if you stir the coffee starts swirling around. That's what the circulating beam of light is doing to empty space. It's causing it to swirl around. But now remember that I said space and time are linked in Einstein's theory. Normally, imagine that you have a piece of paper and you draw a straight line on it. And imagine at the bottom of the paper, you put the past. The middle of the paper, you put the present. And at the top of the line, you put the future. Okay? All of us live along this timeline, from the past to the present to the future. Okay. Now, however, suppose that I could twist the space of that this straight line is in into a loop.
Yeah.
Now you can get what happens. If I can twist it into a loop, then I can start out at the past. I can move along that curve to the present. I continue along that curve to the future. But remember, I've twisted time into a loop. So I can go from the future back to the past. So by twisting space, I can twist time into a loop. And this loop in time can allow me to go back into the past. So what I found in my work is that by using a circulating beam of laser light, you could actually cause a twisting of space.
Yeah.
And eventually you could cause a twisting of time. And so that was essentially you might say what I did was I created the possibility of a laser-driven time machine.
In terms of laser, you mentioned laser, but is this a particular laser? Can you tell me the technology behind, in few words, behind this laser?
I'm sorry. Well, you mean the laser light?
Yeah, the laser. The laser. What is the material behind the laser?
Oh, yeah. That's a very key point. Remember that in Einstein's theory, another aspect of it is that matter, energy are equivalent. Light doesn't have any matter in it, but light has energy. Yeah. And it's the energy of light that creates the gravitational field. Okay. So that's exactly what's happening. Okay. It's the energy of the light that's creating the gravitational field. And the thing is however, I have to, caution people, even though matter and energy are equivalent, that doesn't mean they're the same thing, okay? Mm-hmm. Light has properties that matter doesn't, so they're not identical. Equivalence doesn't mean identical, okay? So there are aspects of light that are different from aspects of matter, and that shows up when you're looking at, the possibility. I mean, I won't go into the technical aspects of it, but mathematically, it turns out that light has properties that matter doesn't. So circulating matter could cause that. In other words, a rotating black hole has that same sort of effect. A rotating black hole can cause a twisting of space. It can cause a twisting of time. Okay. And in fact, that was the analogy that I had in mind when I was looking at the ring laser. But as I said, there's some equivalence, but they're not identical.
So you mentioned black holes. Black holes and wormhole can be a sort of space-time road for passing from one universe into another one in different times. So a wormhole can be visualized as a tunnel with two ends at separate points in space-time. So what do you think in terms of wormhole? So there are these wormholes, black holes. So I know that LIGO, Virgo interferometers for gravitational waves discovered gravitational waves that are connected with black holes.
Yeah. Well, what they found out in that famous experiment that won the Nobel Prize back in 2017 was that if you have two black holes colliding with each other, they will cause ripples in space. And remember that it's the space, essentially the vibrations of space, or the vibration, this is the gravity waves. Essentially, it's the same thing, okay? Because the curving of space is gravity. Incidentally, let me point out something that sometimes popularizers get wrong. Sometimes, not all, but sometimes, Gravity does not cause the bending of space.
Yeah.
Gravity is the bending of space. That seems like a very small point. Gravity does not cause the bending of space. Gravity is the bending of space. And so that was just another verification of Einstein's theory. Einstein had predicted these gravity waves over 100 years ago, but we didn't have the technology to develop it until very, very recently. Okay, and that's another thing that people don't realize is just that technology and science work together. Sometimes you can have scientific predictions, but you may not have the technology to actually see them. But now coming back to wormholes, you're absolutely right that essentially wormholes are like two holes in space that are connected by a tunnel. And that is actually part of Einstein's theory says they are possible. We haven't seen a wormhole, they're possible. And there are things that you can do to manipulate a wormhole so that it could lead to a tunnel that allow you to go back into the past as well. So theoretically, at least, you could travel back into the past with wormholes. There's actually another theory that was developed by a man named Richard Gott at Princeton, in which what he did was to look at, let's say, these were called cosmic strings. After the Big Bang, it was assumed that there might be these fault lines in the universe, and that if these matter fault lines, if they pass each other, they could actually cause a twisting of space and time. And so this is another thing. But once again, we haven't seen these. And then there's the rotating black holes. Black holes, you know, are essentially a star that has collapsed to a point that it traps light due to the strong gravitational field. Okay, when a star collapses, the gravity gets so great that light gets pulled back in. It turns out that the gravitational field is so strong that it causes time to slow down. Okay, but in addition to that, if you have a rotating black hole, that rotating black hole can actually cause space to become twisted. Remember, once again, as I said, if you twist space strongly enough, you can actually twist time into a loop. So theoretically, a rotating black hole could allow one to travel back to the past. I should mention there's a distinction. If the black hole is not rotating, if you go into it, you're history. There's nothing to happen. You can't get out. But if it's a rotating black hole, there are certain directions that you can travel into the rotating black hole and come back out of the rotating black hole and end up in the past. So a rotating black hole could actually be a time machine to the past. But ordinary non-rotating ones could allow you to go to the future just by the slowing down of time.
Fantastic. So now is a science fiction, but one day will be realized, I guess. I mean, time travel. So which are the consequences if we can travel by time? We can change the time. If time travel will be discovered, don't think that now we should see time travelers. So, and how can artificial intelligence, AI, help for this technology? So the next Einstein wouldn't be a human, but an AI, I guess.
Well, the thing is that there's two issues that are involved with time travel to the past. Time travel to the future is something that, as I said, we've been able to do, and there's no paradox. Time travel to the past leads to the possibility of a paradox, okay? Because if you go back, and there's the very, very famous one, it's known as the grandfather paradox, that if you go back into the past and you prevent your grandparents from meeting each other, then they don't have your parents. And if they don't have your parents don't have you. And so if you don't exist, how were you able to go back? Sure. And that's one problem with traveling back into the past. It turns out that remember what we've been talking about so far is relativity. The other major pillar is quantum physics. Quantum physics is a whole different animal, and quantum physics in some ways is even stranger than relativity. Quantum mechanics says that even if we think we have sufficient information at a particular point, we can never have enough information to make an exact prediction of the future. All we can do is talk about the probability of something happening, okay? And this implies a whole different aspect about how the universe may work. Back in 1957, there was a man named Hugh Everett III. And what he did was to apply the notion of quantum mechanics to the universe as a whole. And what he arrived at was the fact that because of this probability aspect, anything that you do, any decision that you make, that decision and its alternative both occur, but in a different universe. For example, suppose that today you were at a restaurant and you saw you had on your menu item A and item B. And suppose you decided to have item B. At that instant, according to Everett's theory, there would be a split of the universe. There would actually now be two separate universes, one in which you've chosen item B and a separate you that chose item A. They wouldn't know about each other, and they're both real universes. And this is happening for everyone. This is all mathematically, it's happening in sort of a super space, okay? But every decision that everyone is making is causing these splits. Now, there was a physicist that named David Deutsch at Oxford University. And what he did was he actually applied the original name for Everett's theory was the many worlds interpretation. We now think of it as a parallel world interpretation.
Yeah.
But now what Deutsch did was to apply that to time travel. And what he found mathematically is that when you arrive in the past, as soon as you arrive in the past, there's a split. You will arrive in a parallel universe. And in that universe, you could actually prevent your grandparents from meeting each other. But that doesn't lead to a contradiction because you were never born in that universe. You would just simply find yourself in a universe in which you were never born. Remember, I said there was a split. When the other universe, you don't arrive in at all. And in that universe, your grandparents meet each other, have your parents, and have you. So that resolves the paradox, okay? This notion of parallel universe. What it says is that time travel to the past is possible, but the universe you arrive in is not the universe that you came from, okay? That's one possibility. Of course, it may turn out that when you do travel back to the past, even though it sounds like it could lead to, paradoxes, we may actually alter our real timeline, okay? What does that mean and how would that look? We'll only know when we do the experiments, but that's, one possibility associated with it. Now, another question that sometimes people have asked is that, well, time travel to the past is possible. How come we're not seeing time travelers all over the place? Well, you have to realize that time travel to the past has a limitation. You can only go back to the past to the point of the process that created the loops. For example, the rotating black hole, I said, could create loops in time.
Yeah.
So you could travel back to the past, but you can't travel back to the past before the black hole was created, okay? And even with my work, you can't go back earlier than the time you turned on the device. So if you turned on the device today and leave the circulating beam of light on, let's say for 10 years, you could travel back 7 years, 5 years, all the way up to the point which machine was turned on, but you can't go earlier than that. So there is a fundamental limitation to how far back in the past that you go. It will depend on when the device was turned on.
Yeah. So just last one. So I can stay here until tomorrow to talk with you. This is very nice to listen you about this great topic. Thanks a lot. Just one consideration, one comment, one question for you.
Sure.
So artificial intelligence, quantum, you mentioned quantum physics, quantum computers, for example. So the next technologies, so would be a good boost for reaching the goal of time travel, or anyway, just to build a sort of time machine.
Yeah, well, quantum mechanics is going to be important for understanding and helping to the possibility to develop a time machine. Exactly in what way is not clear, but it will definitely be something that's very important.
Yeah. Thanks a lot for this great conversation. So thanks and congratulations for your career. Thanks a lot. And so it's been a pleasure to talk with you. Thanks a lot, Ronald.
Thank you very much. Okay, goodbye.
Bye. Stay tuned.